Okay, so now we're going to get started in Module 4, which is all about different depositional systems that we'll see in seismic and how we could use seismic attributes to better understand them, how to have more confidence in our seismic interpretations. Okay, so let's get started. So one of the first things I always mention and try to remind people is that you want to know the system that you're working in. And so this first one that I'm going to be presenting is Fluvial Deltaic systems. So we want to just remind ourselves that we may be looking at distributary channels, crevice splays, delta floodplains, mouth bars, and so there's a lot of different smaller scale features that go along with these deltaic systems that we want to keep in mind that we will be able to pick up in seismic data. We also want to think about the types of lithologies that we would have in the area we're interpreting. And so in this case, we can kind of look at this image over here on the right-hand side, keeping in mind that these are primarily clastic systems. So we'll have shales, silts, sands, maybe even some gravels in like the channels, perhaps, as you can see kind of right here. And understanding the difference in the lithologies, the different internal patterns of the specific features will help us better pick out the seismic attributes that we want to use for the analysis. So getting started, here's an example of one of the earliest coherence images that was generated in Aramco back in 1995 for seismic data that was acquired over the South Marsh Island in the Gulf of Mexico shelf. And so this is showing essentially the Paleo-Mississippi River system, where we're kind of more onshore up here, and then we get down into the delta, or moving out into the basin as we move in this direction down to the bottom left. And so this is very similar to the modern Mississippi Birdfoot Delta. And this is an image taken from 1995. And you could see the similarities for sure. Let me go back and forth between the two. And so using these analogs, whether it's the cartoons, kind of diagrams that I showed a few slides ago, or images of modern satellite data, or Google Images is what a lot of my students use nowadays, that really helps prove up and give you more confidence in your interpretation. This is kind of the very, very classic image that's been produced in a lot of textbooks and such, of this horizon slice through the coherence volume for that Proto-Mississippi River system. And so we've got the delta kind of off in this region, and you've even got, oh, I missed it. Where'd it go? Oh, I thought I was going to show an example of a image of some of the tidally reworked areas, modern analog in this region, but my animation isn't working. Sorry about that. You can also see when we zoom into images, again, here where we're still in the South Marsh Island area, we can see different aspects of it. If we're looking at the amplitude data shown on the left, so we wouldn't be as confident as the coherence data shown on the right. And I've shown this example in previous lectures because it's really, I think, solidifies why you want to use seismic attributes, because while we might be able to pick up some of these cross-cutting channel systems in the amplitude data, we wouldn't be as confident in it. Whereas if we just looked at the coherence here in this time slice, we would be very confident in our interpretation. So keep in mind that using the seismic attributes often allows you to have more confidence, which may impact your risking, or your risking of your interpretation in seismic data. Other features that we often see are meandering channels. And so here we're looking at a couple of meandering rivers, the Meander River in Turkey, and then another modern analog in Peru, where we've got the meandering channel, we've got sandbars building up, we've got scroll bars. It even looks like maybe this could be, we've got some oxbows, kind of abandoned channels also in our modern analogs. And so when we go into looking at our seismic data, we want to keep these in mind now, because they could be very important depending on the purposes we're interpreting for. But oftentimes you can have shale plugs that can act as reservoir baffles, so it's important to know about them. And so this is an example of a meandering system where we're kind of doing a seismic geomorphology analysis. So we're zooming into this area in the red box, and we can see the seismic vertically here, the vertical seismic, but then also the seismic kind of on a time slice. And you can see some of the acquisition footprint. This is really shallow data. It's not conventional seismic, but was rather taken with a sparker system at, I think, about 1,000 hertz or so. So we're getting very high resolution data in this case. And so we can do our interpretation based on what we know about the system. So in these areas, we would expect them to be more sand prone. Here we've got more of a shale prone area. Let me see. Wait, I wanted to say one more thing about this. But you can see how when, if one of the purposes you're using seismic attributes is not just for understanding the geology, but you can see how creating displays like this can be really essential for communicating information to other members of your team who may not be geologists, especially in terms of doing overlays like we're doing here, where you can really demonstrate what you're seeing. So even coloring them in from the yellow to being more sand prone, the shale, a grayer color. And so keep in mind some of the display techniques I'll be showing, because they're really good for communicating your results. Other features we may see in fluvial systems are areas where we have some fault-controlled fluvial systems. And so this is an example of that, where we're looking at the RMS amplitude. Here it's plotted more in a grayscale than the rainbow color bar I've shown other examples in. And this is in the Frio, so it's kind of offshore on the western side of the Gulf of Mexico. And what we're looking at here are some areas where we've got our key horizons, but you can see there's a lot of faulting going on in this area, from the main Agua Dulce fault to other smaller scale faults kind of marked in red here. And what the root mean squared data kind of shows us is it highlights a little bit the Agua Dulce fault, but it also shows some of the aspects of the fluvial system and how they may be related. So in this case, we're looking along the F11 horizon to see those fluvial architectural elements. Here's another example, kind of in that same area, but now zooming in with a little bit more interpretation so you can see more of what I'm seeing. And so we've got a channel belt system that is appearing on the RMS amplitude. So you can kind of see it on the left-hand side, but you can definitely see it where it's been highlighted with the dotted line on the right-hand side. And so then knowing about the channel system and what we would expect with such a channel belt, we can pick out some of the point bar areas and then see how it's related to the fault. Here I'm zooming in a little bit more into the green square, those down on the lower left-hand side. So kind of on the terminus of the Agua Dulce fault in this area. We've got a few other faults in the system, but you can start to pick out, in this case, let's focus on this side, as the channel system. And here where we've got crevice splays, we've got some meander loops, one of them which is abandoned, which we would expect in a system like that. And just a few other areas. Here we've got a cutoff. Here it looks like we've got an oxbow marked in orange down here. And then we can see where it kind of intersects, at least on this horizon, with the Agua Dulce fault. Okay, we can also go through, so now we've kind of gone north to northwest Oklahoma, and we're trying to find channels that may interfere with drilling hazards. And so in this case, we've co-rendered spectral elements components at 15, 45, and 75 hertz to try to see if we can image any of these channel features that would be drilling hazards in the kind of Red Fork area. And so as we go through these, I'm going to try to make that animation play again. And so as we go through these and we move down in time, we can see that some of these channels are kind of easy to see in the spectral decomposition method of illuminating small-scale channel features. And so I've mentioned the Red Fork before in previous lectures. This is a really tricky seismic area to work with because these channels are very, very hard to find. Here's the same area looking for those drilling hazards of the Red Fork in northwest Oklahoma, but now looking at coherence. And so you can see some aspects of the channel in this image too. And then GLCM entropy was pretty good for showing those channels also. So remember, this is a textural attribute, and we can see the channel systems in the Red Fork. Another kind of, besides the channel systems and the deltaic systems, oftentimes we come across differential compaction in these fluvial deltaic systems. And so I want to focus on that for the last part of this mini lecture. So one great area to look at for these fluvial channels are in Alberta, Canada. And so what I'm showing here are two cross sections. So we've got A to A prime, B to B prime, kind of shown here on our time slice, where we're kind of shallower in the blue colors, then we go deeper in the red colors. And so it's a very channelized area, which doesn't show up too well. In the time slice, you can see some of those indentations of the channels, kind of trying to point a few of them out with the arrows. And so when we calculate attributes on this seismic data, here we're doing some phantom horizon slices above the cyan horizon. So if I go back, here's the cyan horizon. We're moving 36 milliseconds above it to create those phantom slices. And looking at coherence in this upper right-hand side. And so you could see the channels that were pointed out in the seismic vertical section with the different colored arrows. We can also see what they look like in most positive curvature when we're calculating kind of the longer wavelength of curvature, and then most negative curvature again. And so the curvature really helps us, really works because of the compaction in these channels. So the negative curvature shown on this side is helping delineate kind of like the thalwags and the channel axes. And so we could combine those images together and do a little animation where we move from the curvature to the coherence. So you can see that differential compaction, particularly here, when we co-render those two attributes together, and we can see on the negative curvature the axes channels. Here's another case where we're doing the same thing, just in a different part of the seismic data. So we can animate from the coherence to the curvature, again, seeing those areas where we have more compaction in the channel, so that shale-filled channel. All right, and then another case in the same area showing differential compaction, but now we're looking for sand-filled channels. So we'd be looking for that most positive curvature. And you could kind of see the bump in the seismic if you could see my laser pointer kind of here. So we've got the coherence showing the edge of the channels, and then the most positive curvature will show us where we have that mounding from the sand differential compaction. And so as we co-rendered those, you can clearly see the areas with the most positive curvature and the seismic, the coherence showing the edges of the channels. And so you can, of course, do lovely kind of mini animations just to show this and communicate what you're seeing in seismic to your team. And so here we've got a chair display with a coherence, and then we can pull in the most negative curvature to show us where we have the differential compaction from the shales in the blue. And then from that, we can also show where we have the positive curvature in red, showing that mounding of the more sand-filled channels. And so end up with a lovely co-rendered display that, shows the data pretty well to your team. Okay, so there's of course some pitfalls that can happen, and there's limitations to all algorithms and seismic data too. And so here we're jumping now back to the South Marsh Island, offshore Louisiana, Gulf of Mexico, and we're looking at some channels that are pretty easy to see on the Sobel filter similarity time slice, so a type of coherence. And so we see them really well on the time slice, but when we look at the vertical section, they are very, very, very hard to see. And so you can see here we can kind of image that fault pretty well, but these channels are just showing up as small little blips throughout. Just very, very difficult to see, even vertically exaggerated. And so one way to kind of work around this is to try to combine our geometric attributes, so our similarity, our curvature, in order to enhance what we're being able to see and have confidence of. And so here we've got that co-render of the curvature and the coherence. And one of the things you'll notice, though, is that the curvature, so shown in the red, white, blue color scale, doesn't correspond well to the channels. Okay, and that's because those channels are so subtle that curvature isn't able to pick it up, like we were able to see in that last example in Alberta. Here's another kind of just display. Now we've moved 24 milliseconds deeper, so we've gone down just a little bit from the last one, and a little bit deeper still. And we just see a lot of variation in these channel patterns. And so, this is a very complex system. The channels aren't well defined in the vertical component. So while we can use coherence to pick them out, curvature isn't able to pick up the curvedness because they are so subtle and so different. Okay, and then here we are a little bit deeper still. So we do probably have differential compaction. We have a lot of channels that are changing how the sediments are being transported down into the basin, but it's very complicated. I often liken this area to like a bowl of spaghetti with a lot of kind of channels all overlaying each other, and it's very complicated to peel back a coherent story. Okay, and then here we're going to do a quick animation loop through this area. So going every 6 milliseconds of Sobel filter. Oh, it didn't work. Okay, well, I was going to show a quick one, but I guess not. But it just kind of summarizes what we just saw with having a lot of variation in these channels as we move down. That is very difficult to pick out with a lot of confidence in your seismic interpretation. You can also kind of see in this example an area where we have differential compaction, and in this case we have the coherence time slice, but then also the dip azimuth time slice. And so this is up in the North Sea, where there's a suspected channel levee on the edges of the channels. And, it's because of the seismic data quality, it can be pretty hard to see. So you kind of can see where we've picked out the channel with a nice question mark because it's not quite as clear. And even with the dip azimuth time slice, we're not able to clearly pick out the channel levee. Here we're showing it with the time slice again, but then trying to go down 220 milliseconds. And we'll notice here that we've got the channel still seeming to appear in this deeper section. And that's because of differential compaction that happened lower and then kind of mimicked that channel up higher, if that makes sense. So I think I've shown some examples, and I'll show some more of where you have a geologic feature deeper. And if you have that geometric compaction lower, it ends up shifting everything down, so you kind of get a ghosting of an image. And so the thing you want to keep in mind is that while coherence and curvature can show you a lot of features, you still need to scroll up and down through your seismic data and do a full kind of quality check and just geologic interpretation check. So there's quite a bit of pitfall and algorithm limitations that you can come across. And one of the big things to keep in mind, particularly with channel and fluvial systems, is that curvature is very, very sensitive to channels where you need to have that mounding or you need to have those levees. And so there can be a lot of cases where curvature isn't picking up aspects of your channel unless you have the related mounding. And so here's some examples of where curvature, the channel won't be seen by curvature, whereas here we'll kind of get that dip from compaction above it that will be picked up by curvature, or the mounding. Differential fill, you'll also pick up in curvature if your seismic is quality data enough, and same with stacked channels. And so just to wrap up, these were just some very quick examples. But in general, you can notice that I went through and I used a lot of horizon and straddle slices rather than time slices to illuminate the stratigraphy of these systems. And that's because you want to account for the dip. 3D geometric attributes, so coherence and curvature, were the main ones that I showed. And then there were a few examples of spectral decomposition. So these are the main attributes that really help with fluvial channel discrimination in seismic data. And then you want to keep in mind some of the limitations that you may have with curvature depending on the level of differential compaction that you have or that you don't have. And that also, like in that one case, you can have a channel at a lower level that then kind of gets projected and is picked up by the attributes higher because of the differential compaction. And then thin channels, sometimes you can see them, sometimes you can't. It depends on your quality of seismic data or how much the amplitude changes of the waveform. But you can often illuminate them with spectral decomposition, particularly at the higher frequencies, and then coherence. And I've got more details about that up on my website if you want to kind of dig into the different types of coherence and how they can be used to image thin bed channels. So as always, thanks for listening.